So let's try this again. So when we increase or decrease the wavelength, we're increasing the kinetic energy of the electrons. They're coming off faster. Okay? Brightness made more come off. Changing the wavelength made them come off faster when we made the smaller wavelength. Okay? Now, normal wave theory could not explain this. Because in terms of waves, if you look at a wave like a sound wave, the energy is evenly distributed along the wavefront. So if I increase the amplitude of my wave, okay, notice I'm not changing the wavelength at all. Wavelength is staying the same. I'm just making it brighter, or the sound louder. Well, when you increase the amplitude of a sound wave, a normal wave, you end up having more energy. And that's why, when you have the big 300, 500 amp, speakers, I mean, you feel it, the energy is there, and it just kind of makes your heart just kind of pound a little bit more. I've had houses where it makes the curtains move, on the speakers. Get it going. But that's not what happened here. If we increased the amplitude, we did not increase the amount of energy. What changed the energy? The wavelength, the frequency, the color of the light. Okay? Now, that threw a total wrench into the wave theory. Einstein's only Nobel Prize came from his explanation of this photoelectric effect. And what he said was that the light is, and I consider it the difference between creamy peanut butter and crunchy peanut butter. A sound wave is creamy peanut butter where it's smooth, easy, it's smooth all the way around. Einstein said no, instead the energy is in little tiny packets. It's in chunks. It's not evenly distributed. And he called those chunks photons. If anybody watches Star Trek or anything, they have the photon torpedoes, okay, where they shoot out the high energy laser type thing. So a photon is a tiny packet of energy. That gives light a particle nature. A tiny packet of energy. So is light a particle after all? Was Newton right? Yes. Is light a wave? Was Huygens right? Yes. They were both right in that light has a dual nature. It's both a particle, this is a massless, chargeless particle, but it's a packet of energy that gives it a particle characteristic. So much so that you all have heard of comets, right? And they have a tail, an ice tail that's on the comet. Everybody knows that? What you may not know, though, is that the tail always faces away from the sun. So as it's coming towards the sun, the tail is behind it. But as it's going on the other side of the sun, away from the sun, the tail is actually in front of it. Because of the pressure, in space there's nothing to resist it. There's no force that has to be overcome. So the little tiny pressure that these photons can put on the ice crystals actually move them out in front, always away from the sun. Okay? Photons give light this characteristic. So if I increase the intensity, I make the light brighter. But let's just say we're sticking with green light. So photons are all going to be the same size still. We're just going to have more surface area, so we're going to have more photons. But each photon is the same size. Einstein then took Planck's idea, E equals h nu. And I was actually just reading up on him today just to get, this is 1900s, this was 1905, so we're right, the same time period, okay? But this H, we know that H is equal to 6.626 times 10 to the minus 34th joules. That's a very, very small number, right? But that's the amount that anytime you change the frequency, the energy goes up by this amount. That's the quantized specific amount that is going to go up. Okay? This little bit. But as you continue, but each frequency is going to have a different energy. So as you continue to change the wavelength, continue to change the frequency, the energy constantly changes. But Einstein said what Bohr actually found was the energy of this photon. And E equals h nu, E equals the energy of a single photon. That the energy was related to the frequency, not the amplitude. Sound is related to the amplitude. Electromagnetic radiation is related to the frequency. That's a huge difference. So the takeaway from this activity you just did, if we change the brightness, what does that do to the number of photons? Increases the number of photons. What does it do to the size of the photon? Nothing. If I change the frequency, the color of the light, make the wavelength shorter, the frequency higher, what happens to the energy? It increases. I think that's what I heard. Now, final thing is Einstein's law of photoelectric emission says that the kinetic energy of the photoelectrons is equal to h nu minus W. Not a very complicated equation to win a Nobel Prize with. Okay? What's kinetic energy a measure of? Energy of motion. So in other words, as the electrons are coming across faster and faster, that means they have more kinetic energy, right? We know speed and kinetic energy are related. The faster you're going, the more kinetic energy you have. Okay? So the speed of the electrons coming across is equal to h nu. This is the energy of the photon. Energy of the photon of the light that you're shining in on. Okay? So as you're shining light onto that metal surface, okay, this is h nu coming in. A whole series of photons coming in. Okay? W is how much, it's called the work function. That's the amount of energy it takes to knock the electron off. Now we know the electron's attracted to the proton, to the nucleus. So it's being held to the nucleus. And so we want to knock that off. Well, it's going to take a certain amount of energy to knock that off. Well, when red light, low energy red light comes in, it's too wimpy. It's not strong enough to break it free. And so it just bounces off and nothing happens. It's not until you get to enough energy with an incoming photon, when h nu exactly equals W, the energy of that photon coming in equals the amount of energy it takes to knock the electron off. That's that final column in your table. That's the wavelength where it seems to stop. That's what we call the cutoff frequency. Okay? That's going to be different for every metal because the electrons are held with different strengths. But if we keep this the same, let's just talk about sodium. The work function is going to remain constant if you have the same metal. So as I change and increase the frequency, what happens to the size of my photon? Bigger or smaller? It's going to get bigger, right? The size of the photon is going to get bigger. If I increase the frequency, I increase the energy, the size of the photon. So, as this gets bigger and this stays the same, what happens to the difference between them?
It gets bigger.
It gets bigger. This gets bigger. This stays the same. The difference is going to get bigger and you're going to have more kinetic energy, you're going to have faster electrons. Okay, so when the sodium on your first metal that you did on this activity, as you increase the frequency, the electrons came across faster and faster and faster. Okay, you increase the brightness and more and more of them came across. Yes, sir?
That means that the shorter the wavelength is, there's more energy?
Yes, okay, because look, energy and frequency are directly proportional, but wavelength and frequency are inversely proportional. So as the wavelength gets longer, the frequency gets lower. The lower the frequency, the lower the energy.
So a low wavelength.
A short wavelength is going to have a high frequency. They're always going to be opposite. High frequency is high energy. So when we're talking about Roy G. Biv, okay, this is low energy, right? This is high energy. So what does that mean about the wavelength of red compared to the wavelength of violet? Red, long wavelength. This is a short wavelength. Now, the reason why we're looking at all of this is because we're going to find that all light, when we see the light, all light is produced by electrons moving in these energy levels. Electrons produce all light. So we have to try and figure out then, from the light, how are the electrons, how do they do that? How are they arranged in the atom in order to be able to move and give off these red, teal, violet, violet? How is it giving off this bright line spectrum? When we come in on Monday, this is just something for you to just be excited about, anticipate. When we come in on Monday, we're going to get to look at how Bohr explained how the electron, giving off this kind of light, relate the light to an electron. Okay? So we're going to understand how the electrons are arranged. We're going to find that this entire periodic table, the craziness that it looks like, the chaos that it looks like up here, is all arranged based upon electrons. Everything that happens in the world as far as all energy, when I just ate my peanut M&Ms, okay, loaded my body full of sugar. But that sugar then is going and digesting and going to my cells, and it's going to combine with oxygen and make carbon dioxide and water. But all of those chemical reactions are nothing more than exchanges of electrons. Everything, the wheels of the bus go round and round because of electrons. These little tiny things that we can't even see make everything happen. So we need to understand how they work. If you're finished, you can turn it in and just make a pile on this desk as you leave, right here. Okay, if you're not finished, you can finish it over the weekend. Those of you at home, you have until Sunday night, midnight, in order to get this done.
Mr. Hobbs, I'm in this class, I feel like I can feel my brain getting like